Welcome to more volume by disk examples. So in this example, let's find the volume of the rotational solid formed by rotating the below shaded region about the x-axis. In this case, we are looking at the region that is above the x-axis and below y equals sine of x. Those two functions, or where we first hit this x-axis, is at 0 and at pi. So we are looking for it at the region between 0 and pi. Again, we are rotating about the x-axis. So if we were to draw what this new shape would be, we would have our sine of x up top, sine of x, sort of the mirror image of it below. And then we would have discs around. It'll kind of look like a football almost. So this is the region we are working with. The radius runs from the x-axis to sine of x. So our radius, we are looking at r of x is just the difference between sine of x and the x-axis, so 0, sine of x minus 0, or sine of x. For our disks, so again, for our disk volume, we are looking at dv is equal to pi times r of x squared times dx. Again, that width of the slice is just essentially the differential dx. So we are looking at pi times sine squared of x dx. Again, I didn't label them here. We're starting, the solid starts at x equals 0. The solid ends at x equals pi. So for our overall volume, we will look at the definite interval from 0 to pi of our dv. So the definite interval from 0 to pi of pi times sine squared of x dx. So we are looking at pi times the definite interval from 0 to pi of sine squared of x dx. We have a formula to rewrite sine squared of x in terms of cosine 2x. So I'm going to give myself a little more space for that. 1 moment. So again, we're getting into our integration techniques here. We have an even power of sine x. And so this is when we do our power reducing. So sine squared of x was equal to 1/2 times 1 minus cosine of 2x. So we are looking at pi times the definite interval from 0 to pi of 1/2 times 1 minus cosine of 2x dx. This becomes 1/2 pi times 1 would integrate to x, minus cosine of 2x becomes minus a 1/2 sine of 2x. Then we are evaluating at 0 and pi. So we are looking at 1/2 pi times pi minus 1/2 sine of 2 pi, then subtracting off 0 minus 1/2 sine of 0. That 1/2 pi out front is multiplying everything. Sine of 2 pi is simply 0. Sine of 0 is also 0. So we are just looking at, this winds up giving us 1/2 pi squared as our overall volume. For another example, this time around, we're going to go ahead and rotate our solid around, or find a rotational solid form by rotating a region about the y-axis. So our rotation this time around is going to go about the y-axis. The region that we are looking at, as we are looking at the region between the y-axis and to the right of the y-axis, to the left of tan inverse of x. And then our y values are running from 0 to pi over 4. So in this case, the region that we are looking at we will do our gray region on the right and then just rotate it or do the mirror image on the left. And then we have disks. It kind of winds up looking like a funnel. So our y values were running from 0 to pi over 4. Let me rewrite that off to the side. It got a little crowded in there. So we're running from 0 to pi over 4 in terms of the y values. Then our radius is running out from the y-axis to the x value. So we need to rewrite y equals tan inverse of x. So the radius should be an r of y. It runs from the y-axis to x. Okay. So we need to rewrite y equals tan inverse x as x equals blah, blah, blah. So in this case, that's simply x equals tangent of y. And our radius is r of y is equal to tangent of y minus 0, since we are running from that y-axis out to tangent of y. In other words, our radius is tangent of y. Our cross-sectional disks, we are now looking at horizontal disks. So our disks we have our disk volume, or our little sliver of volume, dv, is equal to pi times the radius in terms of y squared times dy. Again, this time our thickness is dy, not dx. So we have pi times r of y squared times dy. Or dv is equal to pi times tan squared of y dy. For our final volume, we are looking at the volume. Our y values run from 0 to pi over 4. So again, this is the y value runs from 0 to pi over 4. That doesn't look like a pi. 0 to pi over 4. This is to match the fact we are working with dy. Then we have our dv inside, so we have a pi times tan squared of y dy. So we are looking at pi times the integral from 0 to pi over 4 times tan squared of y dy. We have an even power of tangent. So this was when we peeled off a tan squared and replace it with secant squared minus 1. So we are looking at pi times the integral from 0 to pi over 4 of secant squared x minus 1 dy. This becomes pi times secant squared x, simply goes to tangent of x, minus 1, we are looking at minus x, and then evaluating at 0 and pi over 4. So this becomes pi times tangent of pi over 4 minus pi over 4, and then subtracting off tangent of 0 minus 0, all of that being multiplied by the pi out front. Tangent of 0 is just sine of 0 over cosine. Tangent of 0 is 0. So we are looking at pi times tangent of pi over 4 is 1. Sine of pi over 4 and cosine of pi over 4 are both root 2 over 2. So tangent of pi over 4 is 1, then minus pi over 4, that whole thing being multiplied by pi. And so we wind up getting that our volume is pi minus pi squared over 4, or 4 pi minus pi squared all over 4. So this was finding volume where we were taking horizontal disks because we did rotation about the y-axis. So again, if you rotate about the y-axis, we're looking at horizontal disks. If we rotate about the x-axis, we're looking at vertical disks. So be sure you draw your pictures so that you can see precisely which disks we should be working with. All right. In the next videos, we will move on to washers, where our discs no longer have to be solid and can have holes in the middle.